after the lunch break, everyone. And the next talk will be given by Freden from Utah University, and he'll be talking about aspects of growth in Baumslag-Solitar groups.
Thank you, Michael, for inviting me to present today at Symmetry in Newcastle. I'm going to talk about some research that's been about 20 years, really. Our undergraduate university doesn't have any graduate program that offers a bachelor's degree, and none of my colleagues do humanity group theory. So I have students, assistants. I had about we've seen Cayley graphs before. We know what Cayley graphs are. We know what geometric theory is. There's a definition for Cayley graph for those of us who we do an example or two. Let's do an example of a free group on two generators, X and Y. So each dot on the graph represents a group element, and each edge represents it. The X edge here is directed to the right. I did like to put arrows on it, but an X edge is a vertical upwards edge, and the inverses are downwards and upwards. And I can do a direct product of this infinite tree with symmetry like this, so that at every node in the tree, I have a copy of the standard number line. And I'm going to, in the foregoing talk here, I'm going to be talking about, I'm almost thinking about the construction that I'm dealing with. This kind of like a fiber bundle tree. This is a trivial fiber bundle, if you will, because all the fibers are identical and the goal location. The structure I'm going to be thinking about in the future for Baumslag-Solitar groups is a little bit similar to this idea. I just want to keep this idea in mind. Space and fiber. All right, so I'm interested in computing the growth of generated groups. What does that mean? That means, first of all, I want to calculate all the group elements that can be written as a word. Well, all the group elements whose word metric, which is the shortest way to be written as a word in generators. I want to look at all the base of length again. All words, actually all the group elements whose shortest representative is n, and I'm going to call that sigma n. So sigma n denotes the number of group elements. I can turn this into a power series. This is the idea of 1730. Take your set of numbers and encode them into a Taylor series, and you have a single object that represents all that data. So that's a great data compression. So S of Z is the S is for spherical growth series. So I'm looking at all the elements of previous word length n, and I multiply that by Z to get them all. A lot of times, this function can collapse. You'll have a recurrence on the sigmas, and you can get a rational function. That's certainly the case with the groups I just showed you a minute ago. Sometimes we're also interested in the asymptotics of this generating function. And we can take a look of the greatest convergence. That's called the exponent growth, and you can calculate it the usual way by doing series. For geometric idea, for counting problems like this, the sigma n's are all positive integers, and so that type of Taylor series has some very special properties that general analytic enjoy, and we use those. So let's calculate the growth for the standard generating set free group on two generators. So we use recursion to do this. It's an infinite, the set's infinite, of course. For each reduced word length n, there's only finite many words, so I want to count how many there are. So I'm going to exploit symmetry. I'm going to say that this graph is self-similar. I mean, isn't this symmetry in Newcastle, right? This is symmetry in Newcastle. So here's some symmetry right here. I have this tree is composed of 4 of these red components, right? I'm not going to worry about labelings. I'm just going to take a look at this as a graph. All the edge lengths here are 1. And I can easily compute that if this is my big circle here is my identity element, then I can easily see that I've got 1, 2, 3. You can see that there are 4 copies of this red C here, which I'm calling the cone. There's 4 copies. There's one base at X, one base at Y, one base at X inverse, one base at Y inverse. So the entire growth is at one element radius 0. And then I can do 4 of these things. And if I consider an edge length, an edge has length 1, that's the same. And then I see in itself too, this column C consists of 3 copies of itself. So 3 copies of itself. So you get this nice recursion that each cone consists of 3 copies of itself, and with a appending an edge to each one like that. So there's 3 Z's times the CZ's. Okay, so the cone is 1, that's this point right here, and then 3 of these times it on there, and so you get a nice ratio. The entire group was the origin plus 4 of these columns. So you get a nice. All this easy stuff has been done years ago. Groups with rational generated functions like this. I can do the same thing with the direct product of the free group cross C. And it turns out that the growth series for the direct product is in fact the product of the generating functions as Taylor series functions, whether they're in closed form or not. So the asterisk here is ordinary product. And so I already know what the growth of the tree is right there. And then this is the growth of the integer series for the entire product. However, I'm going to look at this example more carefully. When you expand these 2 rational functions back to this power series and multiply them, how do you do that? That's called a convolution product, right? So term by term multiplication for 2 formal power series, or even 2 big polynomials for that matter in one variable. So you write it as a convolution. So if I look at tau as the tree component, how many elements in the tree at distance k from your E as the fiber, that's the cyclic subgroup count. How many elements in the cyclic subgroup are at distance n minus k from its origin? And there's 2. Then I can put this convolution together and I get a formula. Let me show you this convolution idea again. So this sum here of tau k dn minus k looks like this. Here I'm in the tree. If I go out 1, 2, it's here in the tree, and I'm looking at radius, looking at elements who's in the pre-product or the f is free. I can go out 2 in the tree, and I have 1 left over in the fiber. I go out 1 here and 1 here. Okay? Or I can go out none in the tree, and I have 3 spots left over. I go 1, 2, 3, 1, 2, 3. So the red spots here in the fiber. I'm counting those as elements. I can go out 2 units in the tree, 1 unit in the tree, and I have 2 in the fiber. That's the convolution. So you can do a shortcut here for counting. You can say, okay, I can count all the group elements in the tree that are a distance 2 apart, or that are distance 1 from the origin, for instance. That would be this. On those, and that's I know how that works. So I can count this. I can do the direct product. All right. So I'm going to. So this idea about cone types, by the way, this is really this goes to formal language theory. That if you have this countable discrete structure consisting of only cone types, it's probably going to have a rational growth series, and I get Nero theorem for regular languages. This tie those 2 ends together. So there is some computer science actually in the background. So I'm going to apply these ideas to Baumslag-Solitar groups. So Baumslag-Solitar groups are HNN extensions of Z. There are 2 generators. One of them is a stable error. For several of these, we call them BS whatever. Tell you what the answer. But for this special case, the growth series was figured out by Edved Johnson, 1992. Special case was figured out Collins, Edved, 1994. Those are this case here, and those groups are automatic, synchronously automatic, and these groups here, the 1 ends, those are solvable. And those two cases were done in the 90s, and they both have rational growth. So in 1997, Pierre de la Harpe and Grigorchuk posed the problem that let's calculate the growth of BS23. And by this situation, Q is bigger than P, so not this situation. Well, this is a hard problem. It's still open after 25 years. Very little, a few results. All right, so here is our standard BS-PQ. I'm doing a BS23, for instance, here. So here's the presentation. It's B and T are the two generators. T is a stable letter for H and an extension. You get B to the P by T, you get B to the Q. That's the relationship. And this relator, we call it Horowitz. That's actually due to Lee Mosher and Benson Parr in the paper. They call this Horowitz, and I'll explain that in a minute. So here's my relator. T is an upward edge and B is a horizontal edge. Just like in the free group, I have directions. Locally, the Baumslag-Solitar Cayley graph has local directions. Horizontal to the right is B, and T horizontal to the left, the inverse, and yeah, B across 2 and T down. That's the left side of my relator. B3 across the right side of my relator. So that's standard relator. You can glue these relators into sheets horizontally and vertically like this. This is BS24, which is a little bit nicer. So you've got 2 bricks on top and have 4 of them, 2 edges on top of the brick and 4. Okay, so you can keep putting these together. This is not the Cayley graph. This is not the complete Cayley graph, of course, because the Cayley graph needs to have each vertex having valence 4, because my generating set has 4 elements, B and T. For instance, this node in the middle here, it has a B edge going into it. It has a B edge going out of it. It has a T edge going into it, but it doesn't have a T edge. Graph is incomplete, but I'm still gluing these relators to get part of the Cayley graph. And I can glue them together into a bigger sheet like this. So here's a half sheet. This is the origin for the group down here in the lower left, and then along the bottom here, these are the powers of B's. It's a sigma. So this is called a sheet. Here's the T-axis, going up like that. And an interesting thing that you'll see when you start looking at this is that geodesic paths are not what you might think that to get from 0 to be the 27th and so forth. It's faster to go up over. So that's a shorter geodesic. So that's BS24. Also, BS24 has this, when you're assembling these 4 bricks together, they have a nice pattern. For BS23, I'm going to play the same game. I notice, first of all, the pattern is pretty chaotic. Since back over here, I have these nice vertical lines that go all the way down to the bottom, right? Just down, they keep going down forever. That's not the case here. This vertical line just stops after one. I'm sure one that goes 2. So one goes 1. You still have the same idea for geodesics, same up and over across idea, but the chaotic appearance of this sheet is because 2 and 3 are not. And that little bit of number theory is one of the biggest impediments to. All right. I'm going to take this last picture here and I'm going to embed it in the hyperbolic plane using the Poincare upper half. So here was my origin for the whole group. I'm putting it taking the upper half space model. So the Euclidean, the coordinates you see here are Euclidean coordinates, right? Because I don't know how to do intrinsic hyperbolic geometry. I have to stick it in a model and convert it to a model. So anyway, if you declare that the horizontal edges have length 3/2 log 3/2 in hyperbolic space, in hyperbolic metry, 3/2 log 2. Sorry, just log 3/2. Log 3/2 is the arc length of each one of these edges, whether it's vertical or horizontal. You can go back to the slide and do your little calculate the vertical distance here, right? Do the integral, subtract, you're going to get log 3/2. Here, these are all log 3/2. All right, so this sheet has got the same pattern as the as the pattern I had over here before. It's exactly combinatorial pattern, but now it's the edge lengths instead of being 1, they're like log 3 over 2. And if you do that, then you get this nice embedding, geometric embedding into the space model of operating hyperwell space model. And now it's clear why these geodesic paths go up, over, and down. So that's the way hyperbolic geometry works. The vertical arcs, that circular half circles that are perpendicular to the space of infinity on here, perpendicular, those are the geodesic cross with, and this half circle, this partial circle going like this is pretty similar to the geodesics I was showing you. So anyway, we have a there's a geometric aspect to the Solitar groups. They have some inherent hyperbolic geometry built into them. Let's continue on building the graph again. So here's again another sheet here, and here is I call this the horocyclic subgroup. Powers of B is the horocyclic subgroup. Why? Because horizontal lines like this in hypergeometry, hyperbolic geometry, are horocycles. They are not straight. They are not geodesics. They're curved paths. Okay, they look straight to where you put the eyes, but they're not. In the model, this arc is straight, and going straight across is longer. So the same thing is happening here. So I call this cyclic group. This is the horocyclic subgroup because geometrically the cyclic subgroup forms a cycle. The coordinates along it. It's not geodesic to go across that. Long paths along the streamline are not geodesic. You have to go up, over, and down. Taxicab metric, up, over, and down. Piecewise approximation for those geometric geodesics. Okay, one of the things also in computer programs, it's hard to write B superscript -1 when you're actually coding. This one that's kind of a pain in the neck. So anybody's used Gap or whatever. We typically write capital letters as the inverse. So capital. And also, I can think of the monoid, the generating set of a monoid now, and I'm not going to worry about cancellation for the time being. Just look at a monoid, look at words in B and T. Every dot on this graph and the complete graph is a word in B and T. And B about reduction, you can just start doing some work with that. Sometimes that's useful, not doing any reduction. Okay, so anyway, I've got some more here now. As I told you, that, like for instance, there are some missing edges. So just to the right of this dot here is this little patch mark. That's supposed to be an edge in the Cayley graph, or sorry, a vertex in the Cayley graph. It needs to have edges coming out of it. So what you do is you take new Hor bricks, a new sheet, then right here, and so now this vertex has an upward edge and it has an edge going in from the left, going out to the right, and there'll be one from the bottom too. I'm going to have to do another upper branch in a different color, starting from this one, and another one from this one, and then I'm back where I started. So I have 4 upward branches here. I'm going to have 4 new upper branches in each source cycle. So you get a picture that looks like this. So this is actually 2.6 instead of 2.4. So like here's our Hor brick again. Start right here and I do a T, and I go over T, that's the same as 6 cross. So you end up having 6 upper branchings along each one of these source cycles, and you. So the structure of this Cayley graph, of course I've admitted this picture becomes way too busy. I've omitted a lot of stuff. I've only put in 3 upper edges here. There should be 6. Okay. I didn't put any upper edges on this source branching off this one. I didn't put any off these other ones. This one only here has only 1 going up. There should be 4 more. Right? It's too busy. I just don't sit down. So anyway, we see a tree aspect of this, and a fiber line as a fiber. Okay, unlike the direct product of the free group and the fiber here, the horocyclic subgroup, and one of its cosets here, this fiber here, they're actually connected. Whereas in the free group cross, the was not connected to the other. You had to go back to the origin and then. But this does have a tree cross line structure. Now, if I fill in each of these 4 bricks with a 2 cell, so I get a K2 complex, then this K2 magnet complex is actually homomorphic to a tree cross fiber across a line. So it's kind of like it's kind of like fiber bundle, except that it's kind of like a triple fiber bundle in some sense. If I'm not worried about geometry and I'm looking at topology, this K2 complex is a product. So I'm thinking of the tree as the base, and I'm thinking of the four-cyclic subgroup and its cosets, all these lines, as fibers. Okay, so if it was a direct product, I would just do the other thing before. If I wanted to calculate the growth, I would do a convolution product. I'd move in the tree and then I'd move out horizontals, so on and so forth. Okay, that's what I would do. And I would get a picture that looks something like this. So maybe I want to count this dot. There's a dot right here at the end of the arrow, for instance. How do I get there? Oh, I can traverse 1, 2, 3, 4 steps in the tree to get to the source cycle. To get a radius, and I'm going to count whatever the node is one of the things that comprising the count of that radius. Okay, so this idea works geometrically. But this is not a direct product of tree and four-cyclic subgroup. It's not a direct product because Bassler tree is, by the way, the tree is the Bassler tree. It's not a subgroup. Okay, it's just a set. It's not a subgroup. And also the fibers, the four-cyclic subgroup and its cosets, they're not all isometric. They're not all identical. Okay, but I can still use this idea. I can modify this convolution idea and still get some mileage. All right, so to do so, to modify this, I'll get to the modification of it later. But I need to understand the tree and I need to understand the fibers. So let's start with the fibers. Let's review what's known about. Okay, so I'm looking at a sheet again at BS24, and here's my horse. Here on the bottom, all those black dots. All that lovely symmetry that I pointed out to you in the earlier slide can be realized right here. I've seen some patterns here. I'm seeing some blue, cyan blue patterns, and they're all the same blue pattern you're seeing more and more. They're kind of emerging from the here. It's like a little plant that's emerging from the ground. Here's just top edge. Now you get a couple of edges. Now you get 3 edges. Now you get 4 edges. What's going on is each one of these is the same subsimilar object. Actually, it's not quite so similar. It's similar around. And then we have these brown things. And the brown one is easy to realize. I can see the pattern looks like one. It looks the same. The blue one's a little bit different. But anyway, in a 2011 paper that I did with 2 of my students, we show how you can build a blue one of these out of other brown ones and blue ones, and you can build the brown ones out of other blue ones and brown ones. And these are the suffixes for geodesic paths that represent elements in four-cyclic subgroup. So remember, you have to go up, over, and you take down one of these, go down one of the suffixes, paths and suffix. Get down to your group element here and figure out what the radius, what the geodesic length is. So I've got finite many cone types here. I can put this all together and get rational growth for the four-cyclic. So so the horse, when P divides Q, the horse subgroup is always rational growth. And our very own Volker Diekert in the audience and his student here now also discovered this about the same time that we did. They came used independent methods and proved the same result. Okay, so in addition, they also proved that so we both showed that the geodesic normal forms constitute one counter language. Automata language, context-free language, we only have to have one symbol for your stack and your sequence count. Okay, so one of my students, Schofield, who helps co-author this article in 2011, she calculated exactly what the rational growth series were for every situation. All these other cases, there's probably a dozen cases. Let me just show you what she did. So for instance, here is the class BSN 3N. This is an infinite count, right? Notice that N and 3N, N divides 3N. Right? So She visualized in her head the main half sheet, the main sheet there, containing the horse figured out some patterns, like I did on the picture I just showed you, the cyan and brown picture. She did this in her head, and then figured out the context-free grammar that generates those paths as words. So the boldface here these are grammar variables. Okay. Offset of the grammar variable, cap is the grammar variable, and so on and so forth, and the lowercase letters are the group elements. She came up with this, visualized this in her head for each one of these BS PQs or PYSQ. Like I said, there's like 12 or 15 different cases. Did it all in her head, and then we can turn T theorem. We can convert this into a set of equations. Solution of an algebraic function. In this case, it's there. Again, the implications for the grammar variables become equals. These become variables of z. Your b power becomes a z to the l. Little b to the l also becomes a z to the l. From this e to the l power. Epsilon becomes a 1. These ors become pluses, and you get a system's equations, and you can solve variable here, and you can solve it. There's the rational generating function for the cyclic subgroup of BS and green. Now, let me tell you a little bit about Scofield. She has cerebral palsy. She is in a wheelchair. She can barely talk. She can barely write. She express her ideas. She has no way to express her ideas. She's kind of stuck in this broken body. But her geometric visualization is astounding. I just blew me. He was a big help about 10 years ago. All right, so when the fibers in my picture, the horse subgroup, when P divides Q, we figure them all out. They all have rational growth. We have formulas for them, no problem. What about when P fails to divide Q, like BS2-3? BS2, Q is 3. We proved in our paper that there is no set of GDS that form a context-free language. Can't be done. Of any kind of nice recursions in that case, we don't have anything that suggests that the growth is anything but utter chaos. We have some algorithms that we can compute several hundred of the growth coefficients and get a partial series instead of, but series is probably a nasty transcendental function. Can't work with it. I don't know how to deal with the fibers when P divides Q. P fails to divide Q. I can't deal with it. So everybody ignores BS2-3. Ignore everything that's needed about the horse subgroup control. All right. So the Diekert-Lau paper I talked about earlier, they had their principal result was that when P divides Q, in the science case again, you can get they figured out a way to get a geodesic word for any group element, not just horse words, but any group element way out in the street, going along some cycle way far out there. They have a nice way if you input a word for that, I'll do some rewriting and find a geodesic word for it in a nice form, a nice normal form. So I use that in the later work that I'm working on now. Great idea. The algorithm to reduce a generic word to peak normal form is in like it could be done. Lau tells me it's not quite quadratic. It's quadratic. It's like n squared log n. But it's polynomial. Okay, but I can't really use this to compute the growth series for the entire group because there's exponentially many group elements, and I can't reduce all of them in quadratic time and get anything except an exponential. It's entirely unfeasible. Okay, I have a somewhat the idea that I'm talking about in a minute. This convolution idea gives me a faster algorithm, but it still requires exponential time. So a brute force computation would require about like 2.5 to the n exponential time. You want to compute sigma n, it takes 2.5 to the n next steps to do it. This faster algorithm cuts that down to like 1.67 to the n. Still exponential, but it's a little better. But we have a conjecture. We think that the reason that people haven't solved this problem posed by Grigorchuk and De La Harpe is because it doesn't have a nice solution, and the growth series for the entire groups are going to be at least exponentially bound. That's our conjecture. Finding exponential lower bounds, proving exponential lower bounds is you know, one of these things that's really hard to do. I've been thinking about it for a while. I haven't gotten where. That's one of the reasons I come to Australia and talk about the growth. Yes. Okay. So the exact overall growth problem seems pretty hard. We have an algorithm that will do it, but we can only get 37 terms at max. 37 terms before we run out of space, and it takes a week to run it. So this convolution idea can be used to find asymptotics for this one. So I'm going to look at asymptotics instead. Let's look at the radius, the exponent of growth for this group and see what we can do. I can express it in terms of the growth exponent of the first subgroup and the growth exponent of the tree. So let's look at these ideas for this convolution. Sort of like modified convolution. Okay, so I told you earlier that the problem with it's not a direct product. So the fibers of this structure, the horse cycles, the cosets of the cyclic subgroup, they're not all isometric. They have what's called a level. And in fact, Tinker and Lawn in their 2011 paper realized this as well, that you have this level. When you go up in the group, things get close together. It's hyperbolic geometry. When you go down in the group, horizontally, things are far apart. So as you go down, your horse cycles grow faster. I'll show you a second an example of that. So there are two things. Horse cycles are not all isometric. They depend on two things: level and Q codes. Q codes, I'll talk about that. Let's talk about level. A level is a non-negative integer assigned to each horse cycle or to each node in the tree. Right? Instead of giving you a verbal description, let me give you a pictorial description. Here's the tree. These little dotted lines, they don't look like dotted lines. These horizontal dotted lines are not part of the tree. They're just showing level. Okay. So you start at level 0. There's the root of the tree. Okay. I'm thinking of I projected the horse subgroup to this dot, looking at it endwise. Okay. This is the tree. So if I start at level 0, which is black, and I go up, I get something that's level 0. If I start here and I go down, I get something that's level 1. If I'm at level 1 and I go up, I get level 0. If I'm down, I get level 2. I think that's easy enough. If I'm at level 2 and I go down, I get level 3. If I go up, I get level 1. That's the idea behind level, but there's the little fly in the ointment is if I go up from level 0, I still get it. If I go up from level 0, I still get it. So level 0 gives you the idea. It's like the net exponent sum on the t's in the word represents something. It's like the net exponent sum. If you have a bunch of little t's, always going to be level 0. It doesn't look like you don't have a positive level, or you don't have. So that's level. And let me show you an idea. So I'm going to take, for instance, the horse cycle that's invisible to us because I projected at this point. It's coming straight out of my eye. I'm looking at it so directly I can't even see it. I just see the dot. Okay. The horse cycle coming out of this, and let's do the horse cycle that's coming out of this one. And let's look at those sideways so that I actually see the horse cycle coming out, this horse cycle coming out, and this edge projects to a bunch of edges connecting to them. That's the next slide. Okay, here we go. So here's for instance, here's my horse cycle subgroup on the top here. And here's a coset underneath it. And these black edges here are the group edges, joining them by Horvix, right? There's a Horvix here. If you take a look here, there is, if I assign coordinates to the geodesic coordinates to the top and geodesic coordinates to the bottom one, there's a 2-to-1 relationship. The green relationship, where this node here, R, which has length, its geodesic length is R, corresponds to 2 R's. Okay. This R plus 2 corresponds to 2 R plus 2. This R plus 1 corresponds to 2 R plus 2, and so on. So when you go down a level, your horse cyclic subgroup growth, the coset growth, is twice as much, about twice as much as what the original was. Okay. So level L plus 1 child Force cycle of its level L parent grows about Q over T times faster. Here I'm doing BS24, so Q over P is 2. So I have to scale the fiber growth by the level. So my modified convolution formula, I guess I have to tell you have to tell me how many Force cycles are there at level L and a given distance from the origin. I have to figure that out. So what I will do is I will denote chi RL, chi for coset. Chi RL is the number of cosets in the tree, the number of nodes in the tree, 4 simple cosets. Closest point projection from the group origin is R, and levels L. And I need to count these things, okay? Because this is what I'm going to do my convolution based on. That's going to be my going in the tree this many, R many steps, and I'm going to end at one of these, and then all the horses and cosets that end at one of these I can count. Okay. So again, computing is exactly requires some sort of exponential time, which is not. So I'm going to look at estimating this step. So here's my estimate. I have a modified convolution formula. Remember, sigma of n here is all the nodes in the entire group whose distance. And remember, if it was a convolution, it would be the sum of these. It would be this sum with these. Okay, but I am introducing correction factor here. That's taking care of both. Right. So here's my correction factor. What is the speed of thing? Here's the speed of thing right here. Taking all the cosets at level L and the distance K, and I'm scaling them by 2L. It's deeper, but the further down I go, so this 2L should be a factor associated with this number here. I'm going to scale things by 2L. Fibers are all going to scale by 2L. Counts are going to scale by 2L. And I need to count how many there are, and then I'm going to divide by 1 over the total tree count here. I'll put it back in. I want to put it back. This one cancels that one, right? Now it looks like a convolution with a correction factor. Okay. So if I take a look at these, I can do. I see 3 sequences of integers here. I see the B's. I see the taus. B is the fiber, the first subgroup counts. Tau is the tree counts, and I've got this correction factor, B. Okay. I can do, let's make generating functions for all 3 of those things. So the phi function depends on whatever you're inputting here. I can do the formal power series. The t function, I can do the formal power series for the tree. And we've already done the formal power series for the subgroup. That's rational. Okay. Here's my same formula, and then take a look at this here. So this is sigma n. I remember I multiplied by z to the n, and my sum over all n's. This power series, when I put a z to the n, I sum over all the their infinity. I see a convolution product here, and I see the b's convolute with these two. These are both moving by k, and that's moving by n minus k. There's a convolution product right here. And then these guys, the VK and the tau K, they're moving in lockstep. They both depend on K. That's Hadamard. Okay, what's the Hadamard product? Hadamard product of 2 series is you multiply the coefficients pointwise and you make it a series. So the exponent of growth for this entire growth function, base convergence, if you will, can be expressed in this broken down approximately on the asymptotics. Okay, so there's some. I'm talking about things that grow exponentially, things that grow linearly and polynomial. The word I'm just looking at the exponent of growth. So if I take the do the Hadamard-Cauchy root test on this, it's the same as looking at the singularity of these. So all singularity of these it will be the radius. How do you do them? Oh, okay. Well, convolution means one or the other. Take the minimum. Basic versions. And then convolution means you multiply. Okay, so if I'm doing exponent growth, which is the inverse reciprocal radius of convergence, so I want the maximum exponent growth of this and this. Oh, this factor is only 1.3. I already know that. This factor is bigger. I found it. It's at least 2.25. So the max here is only going to be concerned with this product. Okay, so I want to say so on the asymptotic level, the growth exponent of growth for this overall group is going to be the max of the exponent of growth for the correction factor times the growth of the tree. Turns out that the growth factor here has sub-exponential growth. Its exponential growth rate is 1. The exponent of growth for the entire group is the maximum of whatever the tree is times 1. I'm ignoring that will be for a subgroup, which is obviously smaller, bigger. So I have a theorem. The exponent of growth for the subgroup for the VS24 group, the whole group, is the same as that of its weighted adversarial tree. Right. So now I've reduced the problem to just the tree distance. Right. So let's talk about that. So here is the adversarial tree again, and I want to find its generating function. Start at hand. By the way, these edges are weighted. The edges do not all have length 1. They have length 1 or 2 or 3, and so this tree has weighted edges. And so when I say from the origin over here to this child, that's distance 5. 2 plus 3 is 5. Where's the 2 come from? The 2 comes from, well, remember in my group picture, for me, in order for me to go up one of these 4 edges, I have to go across first. I can go straight up here. This is the T edge. Going straight up. Here I had to go do an offset. I had to offset in the horizontal subgroup. I had to go over B and then up. That's length 2. That projects to, going across by the B doesn't show up in the adversarial tree. Doesn't show up, but it shows up in the weighted edge. So I've got weighted edges here, and I need to figure out how to do this. Okay, so you can see the 1, the 2, the 5, and the 12. Here's the 1, do the 0. Five at length 2, 12 at length 3, and so on and so forth. This is just brute force counting them. I could try doing cones like we did for the 3 group. It turns out that these 3 things, these red things here, these are isometric cones. These 2 cones are isometric as well. These 2 cones are isometric as well. Problem is, the cones do not self-generate in a nice predictable fashion like they did for and 1 cone, and each produced 3 copies of itself. When I did the cyan and the brown patterns in the horizontal subgroup, there was 2 cones. You could build each one from parts of the other ones. Well, here turns out to be infinite. So here are my. Let's do formal language here. I'm going to assign a letter, if you will. I'm going to put that in scare quotes. Letter, an alphabet letter for each one of these edgelets. Okay, and here we have T and U have length 1. PT, I'm thinking of that as a separate alphabet letter all by itself, even though it's 2 characters. Why? Because it represents an element of weight. And this is weight. Here's my weight 3. Here's a weight 2. So if I can go back over here, if I know which this is T here, and there's another T right there, and so on and so forth. If I can keep track of this, maybe I can sort through the numbers. So when we talked about the infinite cyclic group as the fiber in the 3 group across infinite cyclic group, each one of those fibers had a unique closest point projection from that fiber to the root of the tree. There was one unique closest point projection. That's the number 0 on the in BS24, that's not the case. If I look at this is supposed to be right here. Here's my horizontal subgroup, B going up and T going up and down. If I do this edge an offset down is the only way to connect this one to that one. Then both of these green stars are closest point projections to the black dot. That's the geodesic path. There's two of them. And these are both relative origin. Two words. You're supposed to think of this as a V shape. If you look at this sideways as a V shaped thing, this is the green edge is going down, forming one side of the V. Blue edge coming up. If I do another offset go up, now I've got three. That guarantees that the original four-cyclic subgroup and either of these source cycles are not asymmetric, because this has 1 0, these have 3 zeros, this one has 3 zeros. Okay. Branching at the node and the weights of that tree depend on the arrangement of relative origins on the underlying coset. Relative origins that are 2 apart. Does it have relative origins that are 4 apart? What's going on here? If I know, I have to keep track of those arrangements. Okay. So yeah, that's the problem. So the obstruction determining growth in BS24, whether it is your if it was the modified convolution work, and if I didn't have to worry about this, if this tree was regular, then we can do these things. So the problem is this weighted Baumslag tree is the problem, right? So I've got some software I'd like to demo here. First of all, let me show you. Here's our alphabet. Here's my alphabet for the tree right here. Okay. T, a word that ends in little t means went up. BT means when you offset up, offset up twice, down, offset down, and so on and so forth. So these are my quote alphabet letters, but I wrote them as doubles and triples because I want to emphasize that they have weight. This is not the same thing. There's a group element called BBT, right? This tree element called BBT is related to it. It projects to it, but it's not quite the same thing. Okay, so here is my concatenation table, my multiplication table. If I have this alphabet and I want to build edges in the tree by gluing these letters together and memorizing the weights to figure out what the growth series is for the tree, I need to be able to know when I can concatenate and when I can't. Okay, I can concatenate a team with itself, no problem. Happy face. I can repeat that upward edge, follow it by an offset upward edge, no problem. Happy face. If I go up, straight up, and then I want to come straight back down, that's free reduction. Those cancel. In the group, remember I was telling you that little t and capital T, I'm looking at monized letter. Now I'm thinking about them canceling. I can't go up and back and get a geodesic letter. That's a cancellation. All these going up and following it by straight down, you can't do that. But you can go up and then you can do an offset down. So I have this nice concatenation table of rules, but the rules are not completely clear. They're ambiguous here in some of these cases. They're ambiguous here. And to keep track of those ambiguous cases, I have to have some other kind of information. So here's the other kind of information. I need to know what the coset type is. So if I go back over here, suppose that I ended right here. My last letter was BBT. I've got a big long word that ends in BBT. And it ended up at a horizontal tree that looked like this. If I open up the horizontal again, the horizontal, look at it, it looks like this. It's got a couple of origins here, a couple of origins here. They are 2 apart here, then there's 6 apart there, and then there's 2 apart there. I can write that as a .2, .6, .2. It's called dot code. Figure it out. I need to know what this happens because I can't do. I don't want to do an offset twice and go up from here because offset 2 and going up has length 3 and going straight up from here is the same thing. It has length 1. That's the whole, in a nutshell, that's the whole issue with this weighted tree business. How do I settle the 1s from 3s? The way that is. So anyway, Jared Adams, which is my other outstanding student, computer science guy, he imagined in his mind's eye a way to compress all this thing. You can have really complicated arrangements of origins, big long documents. They're all palindromic. All the gaps are even length, but you can still have really convoluted arrangements of relative origins and cosets in the tree. It's crazy. So he came up with a way to compress this data. He calls it Q code. So for instance, if this is my it represents the dots represent the origins, relative origins on a horse cycle here. There's a whole bunch of them, right? All separated by 2. That's a pretty long way. That's a pretty long data to store. He can do this logarithmic compression scheme. He stores it like that. It becomes a ternary integer, and we can even. That's not true. Okay.
Eric,
Yes.
can I ask you a question?
Sure.
Are you only recording where the zeros are?
Yes.
Gaps between.
Yes. When you have, yeah,
You can work everything else out.
you can work everything else out. That's right. Work it. I can't work it out. I can work it out by hand. It's forever. I have to do it over. So. Yeah, the zeros are the important thing. Where's the zeros, and how are they separated? Okay. So, let me just so the Q codes act something like a stack. They're stack memory. So I have a big long Q code here. For instance, this Q code here, it's a stack. I'm thinking the Q is the top of the stack. I'm going to push and pop stuff here from the Q side, right? That stuff. The weird thing is, though, it's not quite a stack. I can push and pop characters from the top of the stack, but there's also what's called a carry operation. So it's like kind of like an addition with carry. If these were all twos, and I wanted to do a certain operation, add a certain edge to it, I'm going to have to round all those twos to ones and put another one on the edge. Really, it's kind of weird. Okay, it's a stack with three symbols. So, given a word W in the tree language, can I extend it by a letter BBT? Okay, that was a question mark in my concatenation table. I've got a word that ends in something, and I want to know: can I add a BBT? It ended in a BT, in a little t. Can I add a BBT? Question. I don't know. I have to go back. I have to find the Q code that corresponded to the letter that BBT. So let's stop my share and let me show you. I didn't disconnect myself.
We can still see you.
You're doing good. Excellent. Okay, so this is some code that my student. So let's suppose I've got it. Here's a sequence. I've gone up, sit down. Let's go another down. Let's go another down. Let's go BT. Okay, is that accepted? Yes, it is. Yes, it is. So here I start with an empty. Just the Q, dot Q, or whatever, 0Q. And then I did a BT, that changed the Q code to 10Q. P, that pushes another 0 on it. That's 100. That pushes a 0, I get 1000Q. And then if I do a BBT, then it's going to pop this 0 and change the 0 to 1. Now, let's see. Can I what is the dot code for that? 101Q. Oh, that's our .2.6.2 just showing. Okay. Can I take this word that I typed in? Can I add another BBT to it? I do. Instead of that, can I put a U on it? Yes, I can. There's my new Q code. So this handy dandy little software here, which runs in linear time and linear space, is really useful or as one of our ingredients in calculating the growth for the entire group. All right. So I demoed that on a laptop. So here's what we proved so far. So every vertex in the Bassett tree, that's a horizontal, whatever. So it's got a unique Q code, which we interpret. We can write it as a ternary expansion, or we can write it as an integer. Each Q code defines a unique thumb type in the tree. So therefore, then there's a bijection between words and Q codes and integers. So there's implementing. This tree is self-similar. Tree is self-similar. It contains, if I take a look at a cone in that tree, which is just a subtree, that's a certain point, it's going to contain every other cone itself infinitely many times. Every cone contains copies of every other cone infinitely. So you can write my T of Z, which is my generating function for this tree, I can write it as a rational function of a couple of cones along with some other stuff. Okay, I can use this to estimate the tree growth exponent. There's methods I can do some linear algebra, do some substitution to lower upper bounds, and I can get the tree exponent growth here, which is going to be the exponent growth of the effect. I just showed you with my stack and stuff. It's context sensitive, but it's not a context free language. Stack was not a context free thing. It's not context free. I don't know. I want to determine what the class. So that's what I've proved so far. Future goal is determine the language class. What is etal? Is it not? Is it worse than that? It is context sensitive, but I don't know everything's context. I want to show that the computation that I have in mind is in some sense best possible. In other words, any other computation scheme for growth, for calculating the growth of the group is reducible to mine in some sense, and so they all have exponential complexity. So I can answer Grigorchuk and Daylogg's problem for BS2 board, say, hey, it's the growth series is intractable, it has exponential, it takes exponential time to do it. Done. Okay, that's good. Determine if the growth exponent growth is transcendental number or not. I think it is. Unpleasant thought, just because it's hard to compute. Using my method doesn't mean it might be easier to compute this exponent growth using another. It could very well be too that the exponent growth, which is the reciprocal of the greatest convergence, it could very well be that that is a rational number, not rational, but algebraic. It could be a rational number, it could be an algebraic number, and then all the rest of the singularities that are okay. I can extend this to BS2, 10, and so on and so forth. That looks quite feasible. All recursions work in trade. Extend this method to BS2 when P divides Q. For any P divides Q, that looks really hard. When P fails to divide Q.
Feel free to unmute yourself if you have some, or post in a chat and we will read it out.
Estimations are really low.
So
It's not an estimation.
that is an actual lower bound. So the lower bound is computed by I said that every cone in the tree contains every other cone. So I replace all but finally many of them with a standard one that grows more slowly than these other ones, and then I can get lower bound that way. Fortunately, that trick only works once. I can't sharpen it.
Then let's thank Eric one more time. He will have a coffee break now.